In this video, we're going to continue talking about the sensitivity analysis and look at how the changes to the right-hand side or the left-hand side of a constraint impacts on our model solution and the objective function value. If we think it graphically again, the constraints of an LP model define the feasible region of that model. So if we look at in this picture here, this blue area represents the feasible region defined by three constraints. When we talk about the graphical method to solve LP models, we convert those inequalities into equations and draw the lines based on those equations and shade the area based on if it's less than equal to or it's greater than equal to constraint. And that's how we define this feasible region. Now, if you think about it, if you change any part of a constraint, whether it be the left-hand side or the right-hand side, the line that was defined by the equation from that constraint will change for sure. So if you change the left-hand side, the coefficients, then the slope of that line will change. And if you change the right-hand side, then the intercept on this vertical axis will change. So regardless of which part you change to a constraint, the feasible region will change for sure. But whether the optimal solution will change, that depends. Say the current optimal solution occurs at this corner point where this purple line and this red line intersect. So if you recall, this purple and the red line represent the first two constraints. Okay, so if we change the first two constraints, any part of the first two constraints, then this point will move because one or both of those lines will change. But if we change this orange line here, this one here, if we change it, the feasible region will change, but the optimal solution will still be this point. Now let's use this graphical representation again to see how changes to the right-hand side or the left-hand side of the constraint impact on our solution and the objective function value. So we mentioned that this original optimal solution occurs at this point where the purple line and the red line, which represent the first two constraints, intersect. Okay, so if we change the first one, the original right-hand side is 200. Let's change it to 201. If you fix your eyes on this red line here and see what happens. You see, it moved outward a little bit, right? And the objective function value changed. And if you keep changing it, 2, then it went up a little bit. And then 2.3, what happens? So you see this green line kept going up because this red line also is moving outward. Now if we change to 2.7, see what happens. So at this point, you see if our right-hand side of that first constraint becomes 207, then all those three lines defined by those three constraints, they intersect at the same point. So this one point, this one corner point is the optimal solution. Now if we keep increasing it, then you can see this red line moves out a little bit. And if you look at the objective function value, it didn't really change. So I'm going back to 207. Okay, so you see when I go back to 207, the optimal solutions and the objective function value are the same as when I change this right-hand side to 208. So there exists this point where when you keep changing the right-hand side of your constraints, it will no longer have an impact on your optimal objective function value and the solutions. Okay, so now let's change it back. And we can look at another one. For example, there's a purple line here. Purple line original value, right-hand side is 1566. So if we change it to 1600, you see what happens? the optimal solution moved, right? And the objective function also moved. And if we keep changing it to 1700, then it keeps going all the way down to this point. And you can probably predict there will be one point where it will move out, and this corner point becomes optimal solution. Okay, so now I'm going back. 1566 was the original value. But let's take a look at what happens when we change the right-hand side of this orange line. So this orange line represents the third constraint. It defines this part of the feasible region. So this edge of the feasible region is defined by this third constraint. However, it does not define where the optimal solution is. Now if we increase it, so it's 2880, right? So now we change it to say 2890. And you can see the feasible region get enlarged a little bit, and but the optimal solution and the current objective function value did not change, because this point did not change. This point still hold as the optimal solution point. So if we keep changing this one to 3000, you can see that the feasible region keep getting enlarged, but our optimal solution did not change. Then what about we decrease it? Current value is 2880. Okay, it's here. And if we decrease to, for example, 2500, did you see what happened? This optimal solution get changed, right? So this line originally did not define where the optimal solution is. Now plays a role in defining where our optimal solution is. And this red line becomes a redundant constraint. Okay, so we didn't change this red line or the purple line at all. What we changed is the third constraint, right-hand side. Originally, we had 2,880 units of tubing available. And now, after we change it to only 2,500 units available, the optimal solution gets changed. And this constraint here becomes the one that defines where the optimal solution is. So with this, let's talk about what kind of information that the sensitivity report will give us regarding to the right-hand side of the constraints. So we're going to move down to the third table presented in the sensitivity report. Previously, we talked about what the first and the second table focusing on the allowable increase decrease parts. And now we're going to move to this third table and focus on what this section indicates. So when we look at the changes in the constraint right-hand side, there's one concept that I like to introduce, the shadow price. Okay, so if you look at the sensitivity report, it's here, the shadow price. So what is the shadow price? Shadow price of a constraint indicates the amount by which the objective function value changes given a unit increase in the right-hand side value of the constraint, assuming all other coefficients remain constant. So the shadow price tells you how much your objective function value will change if you change the right-hand side of a constraint. So if you think about it in the context of the Blue Ridge hot tub problem, the right-hand side of your constraint represents the unit of resources available. Okay, so the shadow price is saying that how much you can gain in your total profit if you get more resources available. So this shadow price here represents how much this final value, your objective function value, will change given 1 unit of change to your right-hand side. Okay, so in this table here, it lists what's the final value of your left-hand side and what's your right-hand side value. And in between these two, so the left-hand side and the right-hand side, and in between these two, there's this column called this shadow price. And this shadow price indicates how much impact this right-hand side change will bring to this objective function value. So for example, if you increase your right-hand side of this first constraint by 1 unit, okay, currently it's 200. It's the x1 plus x2 less than or equal to 200 constraint. And if you change the right-hand side, making it to be x1 plus x2 less than or equal to 201, then you are increasing the right-hand side by 1 unit. And this 1 unit of increase will bring 200 units of increase to your final value of your objective function. So interpreting this in the context of that problem, we're saying that currently we have 200 pumps. And if we get 1 more pump available, then we can increase our total profit from $66,100 to $66,300 because we're going to bring 200 increase to this final value. Similarly, if we look at this second constraint, okay, currently we have 1,566 units of labor available, and the shadow price of it is 17. So what does this mean? It means that if we can have 1 more unit of labor, increasing this from 1566 to 1567, then we can increase our total profit by $17. And if you think about it, these two constraints are the two that define our current optimal solution. And if you change the right-hand side of them, you increase your feasible region outward, right? And that green dot representing the optimal solution will move a little bit. And as a result, your objective function value, which is represented by the intercept divided by the coefficient, will increase too. So, and how much that intercept increase depends on this shadow price. Okay, so the unit of increase to your objective function value is defined by the shadow price. Shadow price hold only when the right-hand side changes within the range defined by the allowable increase and allowable decreases. Okay, so and the shadow prices for non-binding constraints are always 0. So we're talking about this allowable increase and decrease in this table. What do they mean? These allowable increase and decrease are the allowable increase and decrease of the right-hand side of your constraint in order to make sure that your shadow price hold. Okay, so these are the allowable increase and decrease of the right-hand side of your constraint without changing the shadow price. Note that here they are not the allowable increase and decrease for the right-hand side without changing the solution or without changing the optimal objective function value, because from the early graphical representation, you know that when you change the right-hand side of a constraint, the feasible region change, okay? And if those are the constraints that define the current optimal solution, then your optimal solution will change for sure, and your objective function value will change too. So remember, these allowable increase and allowable decrease are for the shadow price to hold. It's not for the optimal solution to hold. And if you remember, say take this example, the right-hand side of this 200 is 7. If you remember when we did that graphical representation, we changed this right-hand side from 200 to 201, 102 to 207, where all 3 lines defined by those 3 constraints, they intersect at this one point. And that one point becomes that optimal solution. Then if we keep increasing the right-hand side of this first constraint, changing it to 208, then that constraint moved out of the feasible region. Okay, and the shadow price representing the impact on your objective function value will no longer be 200 because it's already out of the feasible region. It becomes redundant. So no matter how much you keep increasing it, it's not going to bring any impact to your solution and your objective function value. See if it makes sense. If you think this way, currently we have 200 pumps, right? And this limitation on the pump is constraining our object function value to increase. So we can't make more money because we only have 200 pumps to use. And we can only make 200 products in total because each of them requires 1 unit of pump. But now we get more. Say we get 1 more pump, so we can make 1 more hot tub, and then we can make more money. But at a certain point, we'll have more than enough pumps to use. And if we keep adding more, that just won't add to more profit. Okay. At that point, for example, the tubing becomes the limiting resources that keeps us from increasing our profit. So if we have to make more money, then we need to increase the tubing resource availability. So this allowable increase of 7 indicates that we can get up to 7 more units of pumps to help keep increasing our total profit. But if we increase the availability of the pumps by more than 7, then will that still impact our objective function value positively? Or how much will that impact on our objective function value? Then we are not sure. The same thing goes to this 234. Currently, this labor constraint is one of the constraints that's limiting our objective function value to go up. And the sensitivity report tells us if you get more labors up to 234 units, then you can keep increasing your total profit by 17 units per increase. Okay, but if you increase more than 234, then you're going to get more than enough labor, and you will no longer be increasing your objective function, which is the total profit. Then let's look at this one. So the third constraint. We know that this third constraint is one that's on the top of that feasible region, and it defines the feasible region, but does not define where the optimal solution is. And so you can take a look at this value here. So in Excel, this big value represents infinity. Okay, so what it tells is that you can keep increasing the availability of tubing, and it's not going to have any impact on your objective function value because the shadow price is 0. So you increase 1 unit, 2 units, all the way to infinite unit of tubing, the objective function value will increase by 0. Makes sense, right? You've already had enough tubing. Okay, so if you look at the left-hand side of your tubing, when the model was solved, your left-hand side representing the amount of tubing used is 2,712 units. And you have 2,880 units available. So you already got some surplus. So some tubing got left. And if you keep increasing the availability of tubing, it's not going to do anything to your total profit. You're not going to make more hot tubs and thus making more money. So this is what it's talking about for non-binding constraints. The shadow price will always be 0. Okay, so here we introduce the concept of a binding constraint. The pumps and the labors, those two constraints are binding constraints because those are the ones that determine where the current optimal solution is. So these two constraints, when you draw the lines based on them, where they intercept is where your current optimal solution sits. Okay, And they are binding because it's their limitation that we can't keep increasing our object function value. So they are binding. The other constraint, the tubing constraint, is a non-binding constraint because the left-hand side of the constraint is different from the right-hand side of the constraint. So we already have some surplus of this resource, and getting more of it won't help with the situation. So this is a non-binding constraint. You can tell that by looking at the difference between the left-hand side and the right-hand side. You see the previous two constraints, the left-hand side of the constraint are the same as the right-hand side of the constraints. Now we can look at this allowable decrease. So the allowable decrease of this constraint is 168. Let's see what happens. 168. Okay. So the original availability for the tubing is 2880. Okay, so that's the original model. And it says the allowable decrease for this third constraint right-hand side is 168. So if we make it equals to 2880 subtract 168, you see what happens? These three lines representing the three constraints intersect at the same point. Okay, so if we keep decreasing it, the allowable increase is 168, right? Can you think about what will happen? Do you see what happens? It's not really obvious. So let's just decrease a little bit more so it looks more obvious to you. Okay, so let me just do, say, for example, subtract 180. Do you see what happens? Currently, this orange line and the purple line are defining the current optimal solution. Okay, make it even bigger so you can see this. Okay, so you see here, this red line becomes redundant. It moved out of the feasible region. Okay, so this actually happened when we decrease this right-hand side of the third constraint by 168.1. Okay, if we just decrease by 168.1, it's already happened. So the red line is already moved out of that feasible region. And now this third constraint, this orange line, becomes a binding constraint, while the red line no longer is binding. Actually, it becomes redundant. So this allowable decrease for this third constraint is for this shadow price to hold. Okay, so when the right-hand side of this constraint decrease more than this value, this shadow price of 0 will no longer hold. It will have a positive shadow price because it will become a binding constraint. So these ones are the same. The allowable decrease for those first two constraints, those represent you can decrease your right-hand side of the constraints by this much, and their shadow price will hold. So for example, currently we have 200 pumps. And if we decrease this by 199, so we take away one pump, okay, our objective function value then will be decreased by 200. So you're going to lose $200 by taking away one pump from here. Similarly, for the labor, you can decrease up to 126 units without changing this shadow price here. So if we take away 100 units of labor, okay, then we're going to decrease our objective function value by 17 multiply 100. So that would be 1,700. So you're going to lose $1,700 if you take away 100 units of the labor. But if someone asks, what about if we take away 150 units of labor? What will be the new objective function value? Then we don't know, okay? Because once it go beyond this allowable decrease, then the shadow price will change. It may change to 0 or change to some other value, but we're not sure. So we can only answer the question when the right-hand side of your constraint change within this given range. And we can tell what the new objective function value is without recalculating it. We don't have to solve the model. We can just tell people, say, hey, if you give me up to 7 more pumps, or if you want to take away up to 26 pumps, then my total profit will be within this range. Okay, will be 66100 subtract 26 multiply 200 and to 66100 plus 7 multiply 200. So that will be the range of my optimal objective function value, my total profit. Same goes to that labor. If you give me more labor, give me up to 234 units of labor, or if you take away 126 units of labor from my resource pool here, I can tell you what my total profit will be. So the total profit will be this current value subtracting the 126 multiply 16 to this current value, adding 234 multiply this shadow price. So that will be the range of my new total profits in the optimal solution when you give me more or take away labors. Okay, so that's the allowable increase, allowable decrease of the right-hand side to make sure that the shadow price will not change. And we talk about when we have a 0 here, that means this is a non-binding constraint. And we can tell either by looking at this 0 or by looking at the difference between these two values. When our left-hand side value is different from the right-hand side value, that means in this case, we did not use up all the resources. These are all the resources available, but we only used a portion of it. We did not use it up. So it still have some left over, then increasing more won't help. Okay, so the shadow prices only indicate the changes that occur to the objective function value as the right-hand side values change. Changing a right-hand side value for a binding constraint, which is the one constraint that defines the current optimal solution point, also changes the feasible region and the optimal solution. Okay, so when we change all those constraints, as long as that constraint is not a redundant constraint, we're going to change the feasible region for sure. But whether we change the optimal solution, then it depends on whether the constraint is a binding constraint, whether that constraint defines that optimal solution point. There can be constraints which are non-binding. They define the feasible region, but does not define the optimal solution points. To find the optimal solution after changing a binding right-hand side value, you must resolve the problem. Okay, when we change the right-hand side of a binding constraint, we know that constraint moved outward and the solution, which was represented by that green dot, also moved. But what's the new point that we have to find out? Okay, if we have only 2 decision variables, we can find out the new points by using the 2 lines represented by the constraint, the 2 constraints. But if we have more than 2 decision variables, then we have to resolve the problem in solver to find out the optimal solution. However, we do know the objective function value by using the shadow price and the unit of changes we are going to have. Okay, so if you are asked to find out what the new objective function value is, you don't really need to resolve the problem. You only need to calculate it using the shadow price and the unit of change for those binding constraints. Okay, and if we change the right-hand side of a non-binding constraint, then we know that the optimal solution will still be the same, as long as we change that right-hand side within the allowable increase and the decrease for that non-binding constraints. Okay, so some other use of shadow price. Here is one problem I'd like you to think about. Suppose we have a new hot tub, okay, the third type the company is trying to develop, and it generates a marginal profit of $320. So when we say it's a marginal profit, it means it already takes consideration of all the costs, like the pumps, everything costs. So that is the net profit. Okay, so the profit is $320. It requires one pump, 8 hours of labor, 13 feet of tubing. And the question is, would it be profitable to produce any? So it's going to use some resources, right? And currently, we only have those resources available, and they are allocated to produce those two types, the EcoSpots and hydroluxes. And we know how much total profit we're going to make using those available resources to produce those two types. And now, if we are going to add a new type, we're not going to get more resources. Okay, so the resources have to come from this current resource pool. We have to take out some of the resources. So if we're going to say produce only one, okay, produce only one Typhoon Lagoon, you have to take out one pump, right? And you have to take out 8 units of labor and 13 feet of tubing. So when you take out those resources from the original resource pool, we know that will be having some impact on our original project function value, which is the total profit. So when you take those out, you're going to make less of the two types, and as a result, make less total profit. From the shadow price, we will be able to know how much impact that will be. So how much we're going to reduce our original total profit. And now it's saying that if you do make 1 unit, it's going to bring $320 of profit. Okay. So will this added $320 be enough to make up for the loss of profit by taking out those resources? I'd like you to think about it.